Today we're going to talk about kinetic, and this review is for kinetic chapter 14. So let's get started. First thing first, we're going to review symbols. Big uppercase M mean molarity, which mean mole of solute over the liter solution. So anytime the question gives you mole and a volume, remember that you're probably turning it into molarity. Next is a concentration. Anytime we're talking about concentration, you need to represent it with a bracket. So concentration of A will be written as bracket A. The rate has a unit. Anytime you're writing the rate, remember that unit is either molarity per seconds or molarity per minute, or it could be also molarity per hour. So that means you need to read the question carefully. The time is not always in seconds. Let's talk about rate of reaction. Reaction rate is the same thing as kinetic. So when we talk about kinetic, we're talking about how fast the reaction is going. So the speed of reaction is always the product per unit time. That's why it's concentration over time, as we set it up here in a previous slide. Okay, the rate is going to depend on these four factors, or if you count the volume, that's about 5. Okay, so the first thing is a physical state of the reactant. If your reactant is a smaller, like the powder versus a solid crystal, the powder would react better because there's more surface area available. On the other hand, the reactant concentrations also speed up the reaction. So that means the more concentrated the reactant are, the reaction is going to be faster, which is related to the gases and the volume. So if you think about volume of the container, when the volume of the container decreases, that means your reactant are closer together. So you can imagine that that's the same thing as the reactant concentration is increasing. So therefore, it's going to speed up the reaction. Next is the temperature. Please do not get confused this with the thermodynamic. In the thermodynamic, depending on the temperature, the reaction could be spontaneous, which means it could happen or it not. Okay, in this case, the temperature for the kinetic is always gonna increase the rate of reaction. So as long as the reaction is gonna happen, if we increase the temperature, the reaction will go faster. The reason it's go faster is because of collision. The collision of the molecule is gonna be increased as the temperature increase. I want you to go back and review the kinetic molecular theory where temperature increase, then kinetic increase. Okay. Last but not least is a catalyst. Catalyst will always increase the reaction rate because it's lower the activation energy. As you can see in the picture here, this one above here is not catalyzed, and then this one on the bottom is catalyzed, and you can see that the activation energy is decreased. Now, activation energy is always measured from the reactant to the peak. Okay, so that's what it is. Next one is this, from the reactant, okay, from the reactant to the product. That is what we talk about in thermodynamics. That's the enthalpy. That's the delta H of the reaction. Notice that delta H of the reaction don't change with the catalyst. Okay, catalyst only change the kinetic, which is the speed of reaction, by lowering the activation energy. It does not change the enthalpy. Okay, next case. I want you guys to notice that the collisions and reaction rate. Okay, so when the collision of the reactant molecule increase, frequency of collision increase, the reaction rate do increase. Now, however, this is not one-to-one. The reason why it's not one-to-one is because of these following pictures. Let's go ahead and take a look. You can see that we have 4 different collisions here, and this one got cut out. You can see that depending on how they do the collision, the reaction could or could not happen. So in this case, you can see that only one of the collision is in the right orientation, thereby the reaction will happen. The other 3, even if they collided, the reaction won't happen. This is referred to the one of the in-class problem that we did, where we said that the frequency of collision is not equal to rate of the reaction. So again, when you have the frequency of collisions not equal to, right, rate of reaction or reaction rate. Okay, why? Because the collision is not in the right orientation, okay, right direction. So not all collision will result in the reaction, okay? Let's go to the next one. Reaction rate, we have briefly mentioned that earlier. So reaction rate is unit is cannot be molarity per second, molarity per minute, or molarity per hour. It is always concentration over time, okay? Now, when we say instantaneous just means it is at that time, okay? So the rate do change depend on time, okay? Instantaneous rate at time equal to 0, that is known as initial rate. Okay, so reactant and product. Let's take a look at the graph here. We'll get into the equilibrium reaction later, which is shown by these two arrows. So anytime reaction show two arrows, that means this reaction is reversible. That means as the reactant turning into product can also turn into reactant. Okay, that's why you should have two arrows here. This arrow is what we usually did. This is a forward reaction. That would be a reverse reaction. And you can see here what's the how the rate are proceeding. So you can see here the rate of forward reaction is going to decrease over time, and the rate of reverse reaction is going to increase over time until they sort of reach that equal rate, which is what we get into when we talk about equilibrium. Okay, take a look here. The reason why this up here is happening is because of this. As the reaction proceeds, your concentration of reactant, your amount of reactant would be decreasing because they are getting used up. Okay, at the same time that reactant is decreasing, your number of product is going to increase because you have more product until they kind of reach the same not the same concentration, but until they kind of like flat out and not changing anymore, they get into constant. This is where we get into equilibrium. Notice that concentration of reactant and product not necessarily the same, but the rate will become the same when we get into equilibrium. This graph will be go over again when we get into equilibrium chapter. All right, let's take a look at the rate law. Okay, so we're gonna do the rate in a several different ways. This is the first way we can do that rate. Okay, so here is a hypothetical equation. 2x plus y is gonna equal to 2z. When you write in the rate equation, it's really easy. All you're gonna do is change, delta mean the change, right? Final minus initials. So change in concentration of reactant over time. But notice that something different is in there. The reactant, when we write the rate, is going to be negative, and the coefficient is going to be dividing down there. Okay, same thing. So for the y, same thing, is a reactant, so it's negative. There is coefficient 1, so there's nothing divided down here. Okay, for the z, there's 2 of them, so that's why you have 2 down there. This is a product, so there's no negative there. Okay, the reason why this is negative is because when you talk about the rate of the delta x is disappearing, you're gonna get a negative. So let's say, for example, when we talk about the rate of x disappearing, okay, or disappearance of x, that is gonna be equal to delta concentration of x over delta t. Okay, so that's what is gonna happen. And then when you plug it in and when you try to solve this, you're gonna get a negative answer because reactant is decreasing over time. So smaller number minus larger number equal negative answer. Okay, so that will get negative. Now on the other hand, when you do the product, you're gonna get a positive answer. Okay, let's continue to look at what happened when we look at the rate of y. Okay, disappearing. Okay, disappearing of y, that is still going to be also concentration on y over delta t. So the question is, how are these two related to each other? Who's going to disappear faster? Okay, that you can just tell by looking at the coefficient here. Every time reaction happening, you're going to need to use 2x for 1y. For that reason, the x is going to disappear faster. Okay, how do we know? Well, you can actually write it as these are all equal to each other. So you can actually say it as this. Negative delta concentration of X over 2 delta T, which is a rate, right? Gonna be equal to the other one, which is negative delta concentration of Y over delta T. Notice that there is no need for the 2, okay? Now you will notice that we have the 2 negative. We can cross out each other because negative negative cancel out. So if you look at this, the rate of disappearing of Y is equal to half, right, of the disappearing of X. So you can see that X will use up faster than the Y, okay, just by looking at the coefficients. Okay, the next rate law is this. It's called reaction order. You're going to say rate is equal to K, concentration of A to the some sort of power, which we'll talk about this, and then B, concentration of B, which is another reactant, to the power. Okay, this N and M you can know only by looking at the data. Or they have to tell you it is a slow rate or rate determining step or elementary step. Then you can look at the coefficients. Otherwise, you can't. You need to look at the data to be able to tell. Okay. And can this be 0? Yes, they could be 0, 1, 2, 3, any number. The most commonly though, you see 0, 1, 2, sometimes 3. Okay. Let's take a look at some examples. So let's get started with this. Okay, so for the easiness, I just pick the easy number. Here, I just say the rate, so you can think that's the rate that product is forming, since these are the positive, okay? So if you're taking a look at it, the easiest way is this, okay? You can see which one is the same, okay? So in this case, A, these two are the same, so you're gonna look for B, what's happening. Now, B go from 1 to 2, that is increasing by 2, time 2. Now you're going to look at the rate, what happening to the rate, right? The rate here is going from 2 to 4, so it's also time 2. So if you look at that, that means this is a one-to-one relationship. That means the rate is going to be, respect to B, is going to be first order, okay? That's going to be first order. Now let's take a look at A. Again, I'm trying to look at the other reactant to be constant. So this is a constant, right? Doesn't change. Here A change by multiplication 2. Now you're going to look at here. What is its change in rate? That's going to be time 4. Okay, so how do we tell? Here is what it is. Time 2, right? Time 4. What is 4? 4 is basically 2 squared. Okay, that means it is a second order because it's squared. So order, reaction order respect to A, sorry, we're working on A, is gonna to be second power. Now if you want to, you can rearrange it and say that it was K concentration of A squared, concentration of B, and that is your rate. Okay, so how do we have, let's say multiple choice, you can just do that, get the answer. Let's say for free response. How do we gonna tell? Because remember, you can't just write the answer on the free response. You got to explain them, okay? And you can't just simply draw the little arrows and do that, especially if your work is not clear. They're not gonna give you credit. So how are you gonna write it? So you're just gonna say is this. You're just gonna say what you see. So we're gonna say that. 1, concentration of X is the same, and concentration of B increase by 2 or time 2, okay? The rate also increase by 2. Thus, the rate is first order with a respect to concentration of A. Okay, like that. Now, can we do for, actually I wrote the wrong guide. Yeah, A is the same, B is double, so I should say B here, right? Because B is the one that is affected by it, not A is still the same. Okay. Now, can we do it another way around for the A second power? Same thing. All you're gonna do is this. You're gonna say B is the same. A is increased, right? We're just switching this, right? And then we're gonna say the rate is increased by 4. Therefore, it is a second order with respect to concentration of A. That's all we're gonna change. Okay. Let's look at another example. We have 3 things. Same thing. Let's try to keep 2 of them the same so that we can tell which one is changing to the rate. Okay. So A and B here is the same. C is double. Rate is also double. Okay. This will happening. That's the first order. So we're gonna say rate, okay, concentration C, first order. You can write 1 or you don't need to write 1. Doesn't really matter. Okay. Now that we found one of them, now we're gonna look for another one. Okay. Try to look for 2 that's the same. See if there is not the same, you can make one, but in this case there is already have the same one, so we're gonna keep that there. Okay. Now we see that A is double. Now you see that in this case this is the same. That means concentration of A is to the 0 order. Okay, because it's a 0 order, when you write the rate law, you don't need to write it there. It's not part of it. Okay. Next one, we're gonna look for the same. This is the same. Okay. Now notice that we're trying to look for B in this case. Okay. A here is not the same. Okay. But you don't have to worry about it because A doesn't really affect the rate. So you can say, Okay. So we're gonna compare B. 1, 2, 3. That's time 3 here. That's a time 9. Okay. 9 is a 3 square. So therefore, B is a second power. Okay. So let's go ahead and put it here. That's my answer. Now, how do I write this? I can still write it like this. Okay. So yeah, except you're gonna have A, B, C here instead of just A and B. All right. Let's go to the next graph. This one look a little bit tricky. For this one, remember that your rate here, the coefficient, not coefficient, sorry, exponent here, you want to make sure that they are the same. So the reason I said it because a lot of time people just look this side and then they were like, okay, 5, 1, that's divided by 5. Not the case. You got to look for the power here. If the exponent is not the same, try to write them the same so that you can tell. Otherwise, it's get a little bit tricky to tell. Okay. So since these are -4, I'm going to go ahead and write this to be -4. Okay. So that's time 10 to the -5, 10 to the -4. So that means this is divided by 10. So that means 0.5. Okay. Now we have the same power, so it's a little bit easier to tell. All right. These two are the same. That's time 2. 0.5 to 1, time 2. That means first order. Okay. Now let's try another one. Okay, first order. Let's try another one. They don't have the same. What do? You can do one or the other one. One of the method is you can try to make a new line using what you already know. So what does that mean? So you see how B, when it time 2, you time 2 here. Okay, so we're going to try to match to this. So B, I'm going to go ahead and try to do time 3. Okay, so if I time 3, what's going to happen to the rate? I'm going to also time 3. Okay, so we're going to say 3. A, rewrite it. We're not going to change it because we don't know how A affects the rate. Okay, 1. Let's go and multiply this. I'm going to still keep that 10 to the -4 so that it's easier to measure here. So I'm going to keep 10 to the -4. That means I'm doing 0.5 times 3. That's 1.5. 5 times 3 is 15. 0.5, that's 1.5. Okay. All right. Now we can compare it. Okay, so let's compare them. Now that A are the same. That time 2. 0.5 to 3 is also time 2. Okay, so that means concentration of A is to the 1 power. Okay, so when you write the rate law, rate is equal to K concentration on A, concentration on B. Okay, let's say you don't know how to write the new line. Is there another way to do it? Yes, definitely. What you're gonna do is you're gonna just do with the exponent that you don't know, and then we're gonna try to look for it. So what you're gonna do is this. You're gonna say rate is equal to K, concentration on A, we don't know, so we can just say X. Concentration on B, we have figured out earlier from the first two try. Okay, so what we're gonna do is we're gonna just divide them. Okay, so we can choose any two trial where A is different because we're gonna try to look for A. So let's say I'm gonna look for from trial 2 and then trial 3. So I'm gonna use this line and this line to tell. Okay, so rate is, I'm gonna do this one first because this one's a bigger number. So I'm gonna say 3.0 times 10 to the negative 4 divided by 1.0 times 10 to the negative 4 equal to K divided by K. K is gonna cancel out, doesn't matter. Okay, make sure you pick up the right one. So I go from the bottom up, so I'm gonna use a bottom up. So 2 divided by 1, this is gonna be 3 over 2. Okay, 2 over 1, the X, this is 3 over 2. Okay, B is just 1, so we're good. This one, that's gonna cancel. This is gonna cancel out. We're gonna get 2 to the X, and this is 3. This is 2/3, right? When you go to this side, right? So I'm gonna just switch it to this side. So you will see that cancel out, leaving you with 2 equal to 2 to the X. That makes X is equal to 1. So you can see we're gonna get the exponent is 1. Okay. All right. That is for looking at the table. Okay. So let's talk about unit K. What is K? K do have a unit. Unlike the equilibrium constants, this K has a unit. So what is this unit? It's going to change according to the order of the reaction. So we have zero order where we don't have any concentration. Let's say what's the rate is. Let's say rate is molarity per second. Okay, always concentration over time. That could be minute, that could be hour. That is going to be equal to, well, K is alone, so therefore K unit should be molarity per second as well. Okay, so let's look at the next one. Right here, same thing. I'm going to go ahead and say that it is molarity per second. Okay, and same thing. This is also molarity per second. All right, we don't know K. We're going to leave K alone first. Let's talk about concentration. Concentration unit is always molarity. Here, molarity squared because it's you're squaring it. Okay, so let's see what K need to be. Well, molarity per seconds, this is already molarity, so that means it just need to multiply by 1 over seconds. You can write it as seconds to the negative 1. That also fine. Okay. K here, what's gonna be? We only want one molarity. We have molarity squared. So that means molarity is gonna on the bottom. Okay, we want second on the bottom too. It's gonna be this way. Or you can write it as molarity to the negative 1, second to the negative 1. Notice for these order, it might not be always seconds. It could be hour, it could be minute. Watch out for the question. For instance, let's go back and take a look at earlier question. So notice earlier question, this is C, rate over minute, okay? And this is a second order. How do we know? A to the 1 power, B to the 1 power. That's a second order. So that means K unit for this one is gonna to be 1 over molarity minute. Okay, another word for writing, per molarity per minute. Okay, that would be the unit for this. Okay, all right. Let's look at the graph. This is another way to tell the rate law by looking at the graph. This is a zero order graph. So zero order graph is gonna be straight line with a concentration versus time graph. The rest will give you a curve graph. Okay. And then zero order equation is gonna be this. Concentration of A to the T at time T is gonna be equal to, since it's a negative slope, it's gonna be negative K T plus concentration of A at the time 0. Okay, if you have forgotten, this is basically just algebra equation where you're writing y equal to mx plus b. Okay, so what does that mean? Your slope is equal to negative k. Remember that. Okay, K, the rate law constants, has a unit, it is always positive. It is not negative, it is always positive. Let's look at the next card. First order. First order is a curve on the A, concentration A versus time. ln is a straight line, and then 1 over A is a curve again. Okay, this equation is written as ln concentration of A at time t equal to negative kt. Again, notice slope is negative k plus ln concentration of A at time 0. Okay, now let's say what if I'm trying to solve for concentration at time A, and then you have ln. Okay, to undo ln, all you're gonna do is you're gonna type e to the. So you're gonna say A to the t is gonna do, you're gonna type e, and then you're gonna type this whole thing that you see here, right here. Okay, so obviously solve this first so that you can just type it e to the, and then you're gonna get your answer, concentration. All right, let's take a look at the next one. Okay, this is a second order graph. Curve, curve, straight line. Second order is the only one we're gonna have a positive slope. Okay, it is with the 1 over A. So it's 1 over A, concentration again, T, equal to, this time is a KT positive, okay, plus 1 over concentration of A naught. That's what you're gonna get. Okay, now, sometime what's gonna happen is on the test, you're gonna get just this A, concentration of A versus time graph. And then they could ask you what order it is. So you might say, well, it's easy. I can draw ln, or I can draw 1 over A graph, and then you can tell. Well, but let's say it's multiple choice. Okay, you can't really do ln as a mental math. This is a little bit harder to do. Okay, so how are we gonna do that? There's another way. It is called half-life. Half-life is a time it takes for material to reduce in half. So let's say if you have 100 of the reactant to start with, let's say 100 molarity to start with, okay, and then the time it takes to get into 50 molarity, right, half, that time is take for it to happen, that is called half-life. And this time is take to go into the 25 molarity, again, that's time, that's called half-life, okay? So let's take a look at the graph. All right, the way you can tell them is really easy. If you look at the half-life, you can see here for the, this is, by the way, first order, zero order reaction. For the zero order reaction is a straight line graph, right? But look at the half-life. Your half-life is changing, okay? It is not always the same. That time is take to cut the first concentration to half versus the next one to half, the next one to half, not the same. First order reaction and the second order reaction are both curved, but again, you can tell based by the half-life, because take a look at this. Your half-life for the first order reaction is the same. It doesn't change. You can see here, right? It is take exactly 2 seconds in this case to change your concentration from 1 molarity to 0.5 molarity. And then so from 0.5 to 0.25, take another 2 seconds. And then from 0.25 to 0.125, let's take another 2 seconds. So rate reaction, rate equations for the half-life, right? The first order doesn't change. In fact, that equation is on the periodic table, and you need to remember that. T half is equal to 0.693 divided by K. Okay, that's how you're gonna be able to find K. All right. Second order, take a look. Your half-life is getting longer and longer. So it's not the same either, because it's depend on the concentration. Okay, all right. Rate law. Remember how we said that first slow and fast? Okay, slow step. Another way for slow step is also called rate, not red, determining step. Okay, so what does that mean? You can use this to write the reaction equation. So what does that mean? Concentration of N2O, right? K times concentration of N2O, that is equal to rate. That's it. Right? That's how you're going to write it. Okay. Next, let's talk about the elementary step. Okay. You have unimolecular, bimolecular, termolecular. That basically means reaction order. All the unimolecular molecular elementary step will give you first order rate law. What does that mean? Unimolecular elementary step is just saying that A go to, let's say, I don't know, B plus C. Okay. Or you can say, oh, let me change it back. Equipment malfunction. Let's see. Okay, so or you can have B go to C. Okay, so that would be unimolecular. Okay, so that means your rate is equal to K times concentration of A, or rate is equal to K times concentration of B. That's what you're gonna get. Okay, let's talk about bimolecular. Bimolecular could be A plus B go to C, or you can just have 2A go to a B. That is also bimolecular. Bimolecular just means you have two reactant, right? Even though it is the same molecule, it is two reactant because they are coefficient of 2. Okay, so that means when you write the rate equation for the first one, it's going to be K times concentration of A times concentration of B. For the second one, is the same thing, K except your A is squared because it's 2. Okay, notice it has to be elementary step for you to write it. Okay, it doesn't work if it overall reaction step. Okay, termolecular, that just means 3. So I'm just making a hypothetical equation. 3A go to B. Okay, so that means rate is equal to K, concentration of A, Q. Okay, let's take a look at the next thing. Reaction graph. All right, you need to know how to read the reaction graph. First thing first, we're going to talk about where is reactant, where is product. This is my reactant, is here, the energy. This is where my product is here. Okay, you can see your product is higher energy than reactant. This is an endothermic reaction. Okay, this is endothermic reaction. All right, how do we know? We can even find the delta X of this. Here's how you find it. Delta X is find from the reactant to the product. So I will probably estimate it. Let's say this is about, I don't know, let's say 2 to 15. So I can say approximately 13 kilojoules. Okay. So I can say that this is delta X is of this reaction is equal to 13 kilojoules per mole reaction. All right. There are two more things that you need to know. Okay. Right here is what we call intermediate, which I'll go over that in a second. What is intermediate? Okay. And next is from the reactant all the way to the top of the bump. This is called activation energy. Okay, there's another one. Is from the intermediate to the top of the bump. This is also another activation energy. What does that mean? That means this is a two-step reaction equation where the first step has larger activation energy, that is probably slow step, and then the second one is the faster step, lower activation energy, and we get into product. This is an endothermic reaction. Okay, this next one is pretty much the same thing. Again, your activation energy is from the bottom to the top of the peak. From the here, right here, these two are activation energy. Right here, from the reactant to the product. Okay, this is the delta H, enthalpy. Okay, this is still endothermic reaction. We can calculate that. All right. Okay, something that you need to know. Let's take a look. This is pretty much the same thing as the other one, except I'm going to label each one. Okay, this is activation energy for the first reaction. This is activation energy for the second reaction. Right here, this is my delta H. Okay, this here at the end, that's product. Here, reactant. Okay, this down here, this is intermediate step. Okay, these top two bump here, these are called transitional state. Okay, both of them the same thing. All right, What does that mean? This is a state where things are changing from the reactant to the product. It's just not really stable form. Is high energy, is unstable. This then change into intermediate and then change into the product. Okay. We probably most likely don't ask this, but you should know how to find the activation energy and also delta H given these questions, which is often seen in a multiple choice and a free response. Okay. All right, let's take a look at these questions. These are for practice questions, so let's see. A graph below represents potential energy occurring in a chemical reaction. Write the letter represents the activated complex. Activated complex is basically your transitional state. That is going to be B. All right. Okay. All right, let's look at the next one. Base your answer to the question 2 and 3 on the potential energy diagram. Okay. Which arrow represents the activation energy for the forward reaction? Okay, forward reaction, reactant turning into product. So forward reaction is reactant to the top of the peak. That is going to be activation energy. So therefore, this is A. If we were looking for, let's say, instead of saying forward, and let's say I'm going to change the question, everything the same, but except it's asking for reverse, then the correct answer would be a D because it is now going from product to the reactant. So the peak to the peak is going to be your activation energy. Okay. The forward reaction best described as, well, let's see, forward reaction, my product is higher energy than my reactant. This is going to be endothermic reaction. Okay, so we know that this is endothermic. So we're going to look for this. So we're going to erase all these exothermic. Look at endo. Endothermic is going to absorb energy. So that's going to go with 4. Okay. According to potential diagram shown above, chemical reaction for forward direction is, again, reactant, product. Product is higher energy. So therefore is known as endothermic reaction, which is going to absorb energy. All right, 5, 6, almost done. Let me zoom in. Okay, in the diagram below, which letter represents activation energy for the reverse, which we just said, reverse direction, that would be a D. Okay, which arrow represents the part of reaction most likely to be affected by addition or catalyst? All right, catalyst affect activation energy because it's gonna lower it. Okay. So, which part is activation energy? That is this bump. So anything that is part of this bump is will be affected, which is in this case B. All right. All right. Again, more picture here. Let's take a look. Okay. I want you to find EA for an catalyzed reaction. I also want you to find EA for catalyzed reaction, and then we want to find delta H of reaction. Okay, let's see if we can figure it out. All right, so how do we find it? Okay, also we're only looking for forward to make things easier. Okay, we're looking for forward reaction. So EA is always from the reactant to the peak, so that would be it. So that is 25. Okay, well, I'm just gonna make a circle. Okay, 25 kilojoule. Catalyst, much shorter, this little peak, that's 10 kilojoules. Okay. Delta H, reactant to the product, that's a 15 kilojoules. Let's say we're gonna do all of them the same, except we are gonna look for reverse. All right, so reverse, we're gonna go product to, so product to the peak, so that means we're gonna add it up. 15 plus 25, that's gonna be 30, 40 kilojoules. That's activation energy needed. Okay, catalyst, same thing. Gonna go bottom to the up. So we're gonna 15 plus 10, that's 35 kilojoules. Delta H, Now going backwards, so product to the reactant now is this peak. So that's a 15 kilojoules. Okay, so it accepts you have 15 kilojoules. Is these two are both 15 kilojoules? So are they the same? No. Forward reaction, your products has a lower energy than a reactant. So this delta H is actually a negative. Okay, let's take a look here. That's what we're supposed to have with this. All right. Last but not least, let's talk about catalase versus intermediate state. Catalase are the molecules or elements that are used to speed up the reaction by lowering activation energy. These are show up as a reactant in the earlier step and use up. These are use up in the earlier step. So reactant they got used up, and then in the later step they are formed back. So catalase are never used up. They will make back. They will reform back. So in this case, if you take a look, first thing first, I'm going to try to write the overall reaction, of course, right? Overall reaction. What happened? You'll see things that show up on both sides. That's gonna cross out. This is gonna cross out. So you're gonna end up with A plus 2B go to F. In this case, you see we have two things that got crossed out, C and I. Okay, I strategically keep them this way because our C is catalase. Okay, if in the AP when they ask you why do you say it's catalase, it's because when I say is used in earlier step, right? Back, reproduce in later step. I is our intermediate. Again, it's not always I just make these up. Okay, so intermediate is used, not used, produce, right? In earlier step is backward, but use up in later step. So pretty much back over this. Let me zoom in so that you can see that. Okay, so that's pretty much what we're talking about. Okay, the role of catalase is to speed up the reaction. So they will use up in the earlier step, but they will be reproduced. So they are never gone. Okay, so that's pretty much for how you do the kinetic. So in the kinetic, you have to remember you're looking at the graph, you're looking at the data. So make sure you're paying attention to those. All right, study hard. See you next video.